talking about sustainability, I think old cities are a good example, and especially Venice. They still solved their transportation problem in the same way they did in the past. And I think we can learn a lot looking back in the history, how people achieved, let's say, sustainable solutions over thousands of years. Coincidentally, in Japan, I stepped over this commercial, and especially more or less focusing on the high quality of this space. I think even looking on all the discussion on saving energy, maximizing optimizing optimizing buildings, maximizing their performance, we still have to consider quality. It's very simple to achieve a non-zero carbon emission-free building. You don't have to put anything in there, but nobody would like to live in there. So in the combination of providing a highly comfortable, highly exciting, enticing space, if it's a commercial one, it should more or less foster, let's say, the efficiency and the productivity of the people in there. And we cannot negotiate, let's say, this quality aspect. So certification labels are really a kind of hype now. And I think LEED was one of the first, started roughly 20 years ago. But there's a certain risk of abusing this kind of systems. Those systems are not a design tool, none of them. Not PREEM, not HQE, not LEED. So it's a good checklist. It was really beneficial for the whole discussion, but it doesn't substitute, let's say, a holistic design approach. And more or less taking a usual product and adding, let's say, green gadgets to it doesn't make a good product at the very end. So, a couple of examples. I think I have to dedicate a couple of my gray hairs to this project, but at the very end, I think it's a nice piece. So it's the Mercedes Museum in Stuttgart. And the funny part was that first they done the exhibition itself, so the design of the exhibition was done. And that was part of the brief for the competition of the building. So the task was to do a building around this exhibition. And Ben van Berkel and his guys did a very good job. But it was a cutting-edge project in a lot of aspects, structurally, and even for mechanical, it was really a very difficult project because, because we have to hide more or less all the technique in the concrete. And if you imagine, we have a lot of steel in this concrete, and then we have to embed all the mechanical systems, air ducts, sprinklers, all the lighting, whatever it was. So let's say site supervision and the coordination on site was really a kind of nightmare. A bank building we did in the past with Danish architects. One of our first high-rise for the Deutsche Post. A project we did with Sana. And it's a very specific project here. We had a very tight budget. And the architect started with a more or less a sandwich, the compound concrete element with insulation in the middle. But it was too expensive. And the site is very specific here. It's a former coal mine. Thank you. So there was a coal, more or less, produced from a depth of 1,200 meters. And they still pump all the water up there because nobody knows what will happen if they flood these old coal mines. So we have a huge amount of water. At 32 degrees Celsius, but it is really contaminated with minerals and other chemicals. So the idea was we put a kind of hydronic piping in the concrete, and we use this heat available by this huge amount of water to do a kind of active insulation of this building. For sure, it's a very specific solution only for that site, but so we were able to put the project back into budget. Another one of our biggest project was this airport with Murphian, and it was not a typical project of us because we more or less stepped in when the schematic design was done. And the problem was that at the presentation of the schematic design, an expert hired by the client more or less teared the whole design. Sorry. Teared the whole design apart. And the architect was really furious after that. It's a $12 billion project. And he said his engineers were assigned him and didn't comment anything. So the problem was that it was a single skin. So it was too noisy, too bright, too glary. And the climatical conditions were awful. So we worked on the improvement of the design, added several layers with specific parameters to improve it. This little project we did for Loyola University in Chicago. And the requirement of the client was, he said, his students, one part is the education, but on the other hand, they should get a kind of socialization because it's typically the first time when these kids are away from home, so they should learn how to live with people, and therefore it's necessary to provide a place where they can meet. And by more or less using all the IT equipment, the internet, he was concerned that the students are sitting in their home and doing all with the PC and not meeting and not talking to each other. So the goal was to do a library which attracts as much people as possible. And looking on the building, it's a very simple building. We have an active slab over here, and the shape of the ceiling is a kind of reflector of the lighting. So this idea of integrating several functions into one component was more or less the driving factor to keep it as simple as possible. And 2 years after the grand opening, the dean was very proud that even at midnight they had up to 1,200 people in their library, and it's more or less at the lake of, here's Lake Michigan, and it's really a gorgeous place to be there. So, what will happen in the future? I think we are out of the discussion, let's say, that green equals self-knitted socks and eating more or less organic food on the countryside. And I think even these poor little guys providing energy for this grid-independent building that will not solve, let's say, our problems. So I think the big challenge, if you look that more and more people are living in cities, so the city itself is one of the biggest challenges, I think, in the near future. Maybe not in mid-Europe, maybe not in this part of the world, but looking, let's say, on Northern Africa, looking on China, looking on India, there is a really amazing growth on the cities. So what are the qualities one needs for cities? And I think density has a certain impact, let's say, on the amount of energy we use for transportation, and has also an impact on, let's say, the quality, the vibrant city life we can achieve. And looking, let's say, on these kind of suburban culture, which was developed from the 70s, I think, till the 90s, it's really devastating. So what are the aspects of green city? I think for sure we have the energy. And especially, I know Germany very well, and Germany, sustainability equals energy. That was the main message for the last 10 years. And now we started to open up, consider additional aspects, and I think we are at the beginning of it. And it's really of essence that we take all these aspects into consideration. So for a city, outdoor comfort has an impact. And for sure, what is the identity? the local identity of a city. Recently, I won a competition for a high-rise in Addis Ababa in Africa. We had the first presentation at the client, and we had a long discussion with the architect how to integrate solar shading. And at the very end, you know, a competition, it's always short on time. At the end, they only get rid of it. So the client had two questions. Where's the exterior shading? I found a good client, he knows what he's talking about. Second question was, where's our African identity? And I think looking on contemporary architecture, we have the problem that, let's say a high-rise in Abu Dhabi looks exactly the same as a high-rise in Stockholm or a high-rise in Hamburg or wherever. And I think that's not really the solution. What is the motivation? For sure we have to do something. I think everybody who predicts what will happen in the near future lies to a certain extent. I think nobody knows it exactly. But we know that something is changing. And I think we should not be keen to do the experiment and wait till we have the final results. So for example, here's the result of one of these calculations. And I'm not sure if you remember the summer of 2003. I think in France died more than 120 people due to very high temperatures in summer. If these calculations are more or less correct, we will have the situation that, let's say in 30 years, a typical summer equals the summer of 2003. So each summer will be more or less in that level. And here's a study of Météo de France, and they try to assess the heat island effect of Paris. So that's Paris area. And here is the Paris area at nighttime hours. And I'm not sure if you can read it, but the temperature in the city area drops down from, let's say at day, we have 32, and at night, 27. If you go out of the city on the countryside, the temperature typically is 7 to 10 degrees lower. And one of our typical principles, approach is that we need the thermal mass of a building, using lower outdoor temperatures during nighttime hours to cool down the thermal mass and have, let's say, a cooling potential for the next day. But in a downtown area where the temperature doesn't drop down during the nighttime hours, we cannot use these kind of principles. So what can we do? In this simulation, they used the green spaces in the city, added high albedo roofs, and added, let's say, green roofers where it's appropriate. So it was a kind of more or less dynamic calculation. And only by these very simple measures, they were able to cut down the nighttime temperatures, really, with a high degree. So there are ways to do something. There's no reason not to do something. So here we have, let's say, the historic approach. That's a downtown area in Damascus. So we have narrow streets, we have greenery and shading. This here is a downdraft tower in Bilbao, more or less picking up the same principles, the same physics, in a, let's say, slightly different shape. So the greens here provide evaporative cooling. Evaporation of water cools down the air, and you get a stream of cold air down, hitting, let's say, the area here, where the people can sit. It's a very efficient thing, very simple, and based on, let's say, physics. So I put a competition in here. Typically I'm a little bit reluctant because talking about something which might be built or not be built is not that exciting, but I think that's a very good example how our work might have an impact on the design. It was together with big architects from Copenhagen, and the task was to develop for this harbor area low to no development, so a emission-free new city quarter. And this scale dependency is very essential. So we need, let's say, an optimized master plan to get optimized buildings in there. As soon as we have, let's say, one bad part in this chain, it's really hard or difficult to achieve highly efficient buildings. So on each step, we have to apply, let's say, a high level of scrutiny to achieve a good result. And even on the master plan, we have this iteration, this iterative process where the architect came up with a massing study, then there is an assessment in terms of solar and daylight access, wind and outside comfort, carbon emissions, and then it's more or less a play back and forth to optimize the design. And maybe it might look like that. So typically we have 3 steps in the optimization process. First, we try to maximize the passive performance of the design, which means wind mitigation, passive heating, maximizing solar gains, or natural ventilation. Then by defining, let's say, the efficiency level of the buildings, then we could discuss about supply strategies. So what kind of more or less systems we will use for distributing energy into the buildings. And that has an impact on what kind of energy resources we might use. It's not really a sequential work because there's a link between each of them, so it's a kind of back and forth. A little problem for this competition was that there was an existing master plan, which from our opinion was not really very optimum. So now we are following one of these blocks. So you can put a block in. At the beginning we discussed, for a city like Helsinki, what is an important impact? And so the lack of sun in the winter period seems to be one of the most crucial things. So we said for south-oriented facades of the neighbors, we want to ensure that a certain amount, hours per day, they get direct sunlight. So we cut the roof that it's sure that this guy will more or less get enough sunlight due to our definition. For the neighbors to the north, we said they need a certain daylight supply, which gave us another shape for the roof. And Big was very straightforward and applied these principles on their design. So here we had calculations for different setups or different areas of the master plan. What is the impact of this shape of the building? And more or less, I think that was the point when it was clear that we will lose this competition, because that was the original master plan. And with our implication, we increased the facade area we have to build by whatever, 30%. But with an internal discussion, but we loved this way of design, so we thought to go on with that. So now we're switching, let's say, from a block or grid scale on this block scale. And the architects developed several different approaches, and we did a brief assessment of them in terms of energy performance, or what kind of program might be hosted in these kind of blocks. So penetrations for circulation purposes, indoor courtyards, and then how that might show up, let's say, in the master plan. What is the ideal program at certain locations in the volumes we created? So office space, more or less, to north and northeast, and the residential parts. And so the architecture more or less showed up out of these design principle, design guidelines. So this protected interior courtyards, which allow for sheltered space in winter and open up in summer. So the natural ventilation when we have moderate outside conditions, and it closes up and switches to a mechanical ventilation in wintertime when we have really harsh outside conditions. I'm deeply convinced that, let's say, an operable window, natural ventilation, is a high value. Because we made the experience that the more individual impact we provide to the people on their own climate, the less complaints we got. It seems to be a kind of human need to be the master of the climate, at least in my own space. And for sure, it's not only energy, also water cycle, so grey water cycle, reuse of water, rainwater harvest. And then when we have optimized the buildings, then we could think about, let's say, energy supply strategies. What kind of energy we might use for more or less covering the needs of the building. And for sure, architectural design is always prototype design. Each site is specific, each environment is specific. And one thing for this area there, they have a couple of ferries, more or less, traveling over the Baltic Sea. So we have a couple of ships, more or less, approaching the harbor each day. And looking on a ship, we have a huge diesel, which rejects all the waste heat into the ocean. So the idea was, why not putting a container with phase change material, which allows for heat storage on the ship, and then take it, put it on a truck, take it out, and use it for cover the heating demand of our city. Otherwise, it would heat up the Baltic Sea. So it makes much more sense if it heats up our buildings. Some impressions. For sure, I think this part might be a little bit difficult. But it was really funny, so it was a kind of a very dynamic process with these guys, and we had a lot of fun in doing this competition. Another one we did with Danish architect from Stuttgart and Gale architects from Copenhagen was a competition on a city block, or 2 city blocks in Pittsburgh. And Jan Gale works a lot on, let's say, making the public realm more attractive. Because he says in the past it was really necessary to go on the streets. You have to go to the market, buy your goods, buy your food. You have to go to work. But nowadays it's not really necessary anymore. You can order your pizza via internet, you can do your job via internet, your bank account. So to get a vibrant city life, to get people on the street, you need certain attractions, an exciting outdoor space. And for sure it has to do with comfort, it has to do with attractions. And he said, this kind of city life is really something valuable you want to achieve, and which exceeds or increases the quality living in a city. So that's the city block, and there's a highway more or less separating the city from the Elite River over there. And one of the ideas was to solve that non-satisfying situation here by covering the street so that it's possible more or less to get direct access to the river, and in addition, due to additional space here on top, to make, let's say, the riverside more attractive. And Pittsburgh is quite harsh in winter, but in summer it's a quite comfortable climate, and a lot of the life is on the exterior. So here you see the different steps covering of the street and providing access to the river. So very simple, very principal rules. We, in terms of city life, the idea of having fairly narrow passages here, widening up to these places, it's an old idea. I think each Italian city with a historic master plan has this kind of setup. Looking on the climatical data, we figured out that especially cold winds in winter approaching the site from this direction. So the idea was to close more or less the site here, providing only small passages and opening up here, because here we have the appreciable summer breeze, improving, let's say, the outdoor conditions. Sunlight for sure was a big deal. So that's the idea of this dense urban experience, which is not really typical in American cities. And what we typically do is, at the beginning, with supporting the architects with massing studies, and now this shading study, we are the sun, and now we're following the sun more or less around the site. So each surface you see now will more or less receive direct sunlight. So we can see at which time of the year we have direct sunlight, especially in the public realm. So we won the competition, and the city is, I think, now in negotiation with the third developer, so we will see what happens. This project suffered a little bit from the financial crisis. I only want to talk very briefly about Master. It's a very ambitious approach. We worked with Foster & Partners and a big team, more or less on maximizing or achieving the very ambitious targets for this project. And the idea is to do a new city in Abu Dhabi, focusing on research. It should be a kind of center for research on renewable energy and sustainability. And it should be more or less emission-free. And here we did a rough assessment of different design approaches. If you see on the perceived temperature, in the desert, we end up, let's say, in summer at roughly 67 degrees. If you look on the typical setup in Abu Dhabi center, it's even worse than in the desert. By applying, let's say, I would say American skyscrapers, you create, let's say, really, you worsen the conditions significantly. Looking back on, let's say, the historic approach in that kind of climate, so these narrow streets and arcades, which are very typical for Arabic towns, we have a significant improvement. And when we add, let's say, in addition, some evaporative cooling, we got more or less close to, let's say, these better conditions. For sure, 40 or 38 degrees are not really comfortable, because typically it's combined with fairly high humidity ratio. But I would say you're able to survive at 71. Nobody will be out there. Here we compared the approach for Master and the conventional city. And I think a very interesting point is the contribution of the buildings. It's the highest reduction potential we have. It's close to 60% or 55%. So by improving the performance of the buildings, it's really one essential step towards a sustainable city. Here we identified the required reduction to make it possible to cover the remaining energy demand by renewables, because the space is limited. So there is no endless space where we can put solar collectors or whatever. So compared to the nowadays typical energy demand of a household in the Arabian Emirates. For example, for residential, we have to cut the demand by more than 80%. So the people are losing more or less 80% of their energy, and only, let's say, 10, 15, 20% will be available to cover their needs. So that means we have to do a lot on the performance of the building, but we have also to work on, let's say, the personal attitudes. We cannot do these big changes only, let's say, by adding sophisticated technology. So that was my first project, therefore it's here. And it was a funny situation because we got into the project when it was more or less done, but the mechanical engineer required a ventilation system for the sports hall, and that blew up the budget completely. So, some impressions. So here we have the ground floor, the locker facilities, and there was a kind of stiffening rib for the floor plate. Here we are one floor up, that's the gym. Some stands for visitors, and here the foyer. And looking, let's say, on this design, it was there like that. We reinterpreted it. So we used the foyer, the fully glazed foyer, as a solar collector preheating ventilation air. So we added a small fan in the partition wall, driven by a PV, and so we take air out of the foyer into the hall in wintertime. The whole thing is driven by this glazed roof, which was integrated to improve the daylight, but also to host the curtain separating two parts of the hall, because due to the curved roof, it was not possible to put it anywhere else. We use it as a solar stack, so the sun is overheating the exhaust air, more or less fostering the stack effect. So we switched from a mechanical ventilation approach to more or less fully natural one. We doubled up this stiffening rib so that we have a kind of duct, and we enter in summer from this side, having a kind of pre-cooling of ventilation air, and then bringing the air at these parts of the wall. And each heat source, even this little spot heated up by the sun, creates a plume, so air is moving up and sucking fresh air out of this fresh air lake. So we have a very efficient ventilation system, which more or less no additional effort. Now, what works for a small building works also for a big building too. And this one is quite ambitious. The client, the KfW Bank, is a public bank in Germany, and they're more or less in charge of all the programs subsidizing energy efficient buildings. So they are very more or less keen to achieve a high level on their own buildings, as an example. And the goal for this high-rise was to achieve an energy consumption less than 100 kilowatt hours per square meter per year, primary energy, which means that, for example, electrical energy is rated by 2.8 in Germany, considering all the energy which is used to produce the electricity. So we ended up, let's say, roughly at 50 kilowatt hours per square meter in year per hour, and energy, which is really ambitious for a high-rise, because we have to cover, let's say, all the circulation, elevators, all this kind of stuff. Looking on the design, because it was funny, there was first the architectural competition, and then we came up on the team on the client side. So this design was more or less there. And here we have the windows of Frankfurt. And if you're looking on this building, the shape is more or less directly into the main wind direction. We only have to switch the building a little bit to get it exactly into that direction. Because the problem on a high-rise is, or I have to add, a company standard is operable windows. All of their buildings have to have operable windows, otherwise it's not possible. So this combination, we have a fairly low energy demand, which is allowed. We have operable windows, which are required. Creates, let's say, a problem as soon as in wintertime we have wind more or less hitting the building. So we got a high pressure zone in the wind direction and a low pressure zone, more or less vice versa. So as soon as somebody opens a window here and another one here, there will be a big rush through the building and we're losing a lot of heat, which more or less we have to avoid to meet the requirements. So the question was how to deal with that problem. The architect had in his design for the competition a fairly simple double skin facade, and we changed it a little bit, more or less to achieve, let's say, a new function for it. The idea is pretty simple. We collect the wind here and redirect it into the double skin facade. We have flaps, controllable flaps at the end here, so we can control the amount of air leaving the double facade. So you might compare it with the tire of a bicycle. If you pump it up, there's more or less the same pressure in this tire at each position. And exactly the same happens here. We have a big pressure drop around the building with high air velocities, but by limiting the velocity in the double skin facade, we reduce this pressure drop to a very low level. So now it doesn't matter if somebody opens a window here or here, it's always possible. So we increased the times where natural ventilation is possible roughly by 80%, adding these principles. The building is now in operation since roughly 3 months. So we have a first feedback, and for sure a certain adjustment is needed, but the first results are really promising. In summer, where we don't care if there's a cross ventilation, we can open up, let's say, all these flaps that we minimize, let's say, the high temperature in the double skin facade. Looking on the building systems, we have an active slab, which is a hydronic tubing used for conditioning purposes, for heating and cooling. We have the natural ventilation, double skin with flaps. We have a optimized mechanical ventilation system, so at harsh outside conditions, we use the mechanical one. But let's say in moderate conditions, we stop the mechanical supply, so we have only the natural ventilation, but the exhaust is more or less the same. That's naturally driven over the stack effect, over the height, so we don't need a fan, let's say, on the exhaust side. Some impressions of the building, and really a nice effect with these flaps and the curved shape of the building is that walking around the building, let's say, these colors or the impression of the building is always changing. So we go to a next high-rise, really a completely different climate. It's in Winnipeg, Manitoba. And checking where Winnipeg, Manitoba is, I realized that we are far up north. It's roughly 1,000 miles north from Chicago. So, and we have really extreme weather conditions. It goes down to minus 35 in winter. They have 4,000 hours below freezing. But even in summer, we have, let's say, a 6 to 10 weeks period where it goes up to 35, 38 degrees, and we really have a high humidity in summer. So we have the combination of really cold in winter, but hot and humid in summer, so it's a really continental climate. Really extraordinary is the solar insolation. So looking on the winter months, we have more or less 2 times the insolation we have in mid-Europe. So we have the combination of a very cold but sunny and bright climate. And the wind direction is really very clear, north-south. So the client toured Europe, Asia, Australia before he started the project itself, because he wanted to know what is more or less state-of-the-art sustainable design all around the world. And we gave these guys a tour and talked to them, and we focused that from our perspective, it's really essential that we focus on the early design phases. Because at that time, you make the important decisions and you have the biggest impact on the cost. And so it was a very untypical project. We started with a charter, so each consultant designed a charter defining the goals for this project, and also the client signed it. And we got 4 months in front of start of the preliminary design, because we could convince the client that more or less this time is the most important, and rushing at that time doesn't pay back. So the architect started with, I think, more than 30 massing studies. We did a rough assessment of each of these studies in terms of energy efficiency, daylight, wind. So we cut them down to 15 options. These 15 options, we did brief calculations to get a closer look on the performance we expected. And then we selected 3 more or less for further assessments. And these 3, we did detailed simulations, and at the very end, Daylight Tower was more or less a slender high-rise. Comfort Tower was the most compact building, so we had the best volume to heat exchanging surface ratio. And at the very end, the solar tower made it. So we have a V-shaped floor plate. It opens up to south, more or less to get as much solar gains as possible, and it closes up to north. This high-rise, I think, was the first high-rise downtown Winnipeg since roughly 20 years, 15 years. So we had a lot of discussions with the neighborhood, which has a big impact on the design, on the permitting process, especially. And so, for example, we did a lot of shading studies. What is the impact on the neighbors? And for sure, let's say, because we have this big south-oriented facade in the main wind direction, so the question was, how is the deviation of the wind? What happens here? And for example, one of our result of these calculation and assessment was a big cantilever roof in front of the main entrance, because the facade creates a downdraft here, so we had very high speeds on a pedestrian level on the main entrance. So we did energy assessments on these options, more or less to provide the selection. And at the very end, we came up with this concept. So we have the south winter garden, which is naturally ventilated even at that harsh climate, roughly 40% of the year. In winter, we're collecting most of the solar gains. It's used as a preheating area for ventilation air. We have small air handling units on each floor, taking air out of the atrium space in an underfloor air distribution. And we have a solar stack going up here. And the solar stack is more or less to travel the exhaust out of the building. The conditioning of the space is done by the active slab. We use it for heating, cooling, cheap and efficient, so that the ventilation air is more focused, more or less covering the hygienic demand of the people in there. The energy supply system is based on 200 80 boreholes underneath the building. We can use from considering the temperature level, the water out of here directly for cooling into the active slabs. We don't need a chiller for cooling. Chiller capacity is only required for dehumidification. And in winter we use the same system for heating purposes with a heat pump. We had a long discussion with the entrepreneur, the general contractor, and we got incredible high prices for this active slab. So at the very end we decided there's no other way. Out of that, we took 3 of these guys to Germany on a construction site and showed them what we're talking about. And they showed up in their typical working dress and looked at a thing and said, well, you put a garden hose in slab? You're kidding? That's easy. Let's do it. And they dropped the price by 80%. So exactly the same happened with this solar air stack, which is nothing else than a simple shaft running high the building. Coincidentally, I saw the cost consultant put in for that. It was in the range of $5 million. And then I was really shocked because we calculated it internally in the team in the range of, let's say, 800 to $1 million. And it was 5 times higher. So I asked him, why is that so fucking expensive? And he said, oh, solar air stack. So it's rocket science, sophisticated, high tech. So that's expensive. So at that meeting we decided that we get rid of the solar. We call it exhaust stack. And then he got down not to 1 million but to 1.5. So we saved 3.5 million a day. We wrapped around double skin facades all around the building because the client told us that more or less each of his real estates suffer of facade damages due to these really harsh conditions. So they have freezing, moldering in winter. And the idea is we have the insulation layer at the exterior. So we have a highly insulated glass outside. And we heating the facade cavity. More or less, we keep it above freezing. Then we have a single pane of glass to the interior. And then we have the fully conditioned space, working space. The facade opens up because, as I said, it's roughly 30% of the year we can do natural ventilation. So we switch off the mechanical system more or less completely. And the facade opens up automatically. And there are sliding doors at the interior, so each individual can control his own work desk climate. A very important part is this south-oriented atrium space. So we have openings at the bottom and at the top. In summer we have a shading, interior shading here, which is ventilated. And we put, I think it's hard to see, we put a water wall in there. So there are little cables running down here. We are talking about roughly 30 meters. And the idea is to provide humidification in winter because we have very low outside temperatures and the air is really dry when it gets in. But we also use it for dehumidification in summer. And it sounds a little bit odd to use water for dehumidification, but it's simple physics. If it's cold enough, then the air condensates more or less at this cold surface, and that's exactly the effect we need. So at the very end, the client started with the requirement, he puts a certain percentage on top of the budget, but he wants to have the greenest, most sustainable building in North America. And what we tried, and we found, let's say, with the architects a partner which was like-minded, and so we tried to incorporate, to integrate this kind of approaches as good as possible into the design. And for example, if you look at this solar stack, and that becomes more or less a signature of the whole building. So for sure it was a discussion how that thing should look like, because the impact of the impression of the building in general was fairly high. You see the atrium space, for sure green roofs. So, roughly 2 years ago, the first employees moved in. Now we have roughly 2,000 people working in that building. The client is really very pleased with, let's say, the press he got with his building, so now they have more than 3,000 visitors. I think it starts to get a little bit exhausting to tour all the people through the building, but they're still so proud that they really love to show what they have now. It was funny, there was an intensive discussion with the employees because they were scared to go downtown. Nobody knows exactly why, but one explanation was they watch too much American TV and get the idea that downtown equals dangerous. But they collected more or less these 2,000 people. They were distributed all over town in small units and collected it in one building. 70% now switched to public transport. And it was a decision by the board not to do a Mensa or cafeteria in the building. They want to more or less improve the city life. They want to improve the little restaurants and things all around the building, which for sure was, let's say, beneficial in the neighborhood meetings because they could offer them, we bring you 2,000 new clients per day. And that might be one of the reasons that the neighborhood meetings went that well. We have the big advantage with that project that we are in charge of a monitoring, so we do a detailed measuring of energy demand and the performance data of the building. We don't achieve the calculated numbers so far, but we're getting really close. So for example, lighting, we are now, compared to the code standard, we saved 56%. Calculated, our goal target is 65. And there are a couple of optimization potentials, and we're in that process more or less to optimize the operation of the building. And even, let's say, from a social point of view, the building is well accepted from the neighborhood. A lot of events are happening in the podium building, in the public part. And it was really funny. At a big opening, I never saw a client which was so proud of his new building. So it was really, yeah, great. Comparing, let's say, the energy demand. So we have to go down to 64. That's the target. There are a couple of reasons we're still more or less higher than that. But the client said even with this number he would be really pleased because comparing it to good practice, that's an average of all Canadian buildings. That's, let's say, measured values for new buildings. That's the code standard. And that's, let's say, the CBIP is more or less a certification label. So those is more or less the level for a highly efficient building. So I think we're not bad with this 88 kilowatt hours. Looking on the press, the client got with his building, I think he's very pleased. It runs through more or less whole America and Europe. We did an exhibition at the design school in Winnipeg, which was really a big success. And we got a couple of awards for it. And my credits to the team. So now we're switching completely. Now we're in the Syria, Damascus. And a French architect approached us and said, I have a nice little project, it's a school, but it's in Damascus. So we discussed who is willing to go to Damascus. It was a long discussion. And the budget is very limited, and it has to be simple, it has to be robust, because the French government donated it to the state of Syria, but they have to cover the operational costs on their own. And those are poor guys, so do what you can. So we dived a little bit into the vernacular architecture there, and these wind catchers is one of a very typical thing there. There are very stable wind conditions, especially in summer. And the idea of this thing is more or less, it's open to the main wind direction. So the wind is collected and then travels down here. So to more or less ventilate the interior courtyard. Here there are typically plants and fountains to provide evaporative cooling to create a pleasant microclimate there. But on the back of this element, it's connected to the upper part, and if the wind hits it here, you get a zone of low pressure on the backside. So also the exhaust is more or less covered by this clever element. We have this picture already, so this microclimate approach. And we got up temperatures, let's say, slightly above 40 degrees for a couple of days per year. But this climate in Damascus, it's fairly dry, arid in summer. So let's say evaporative cooling is a very efficient measure to mitigate, let's say, maximum outside air temperatures. That's a model of the setup. So the idea was to do little houses. So each house hosts 2 classrooms. So we have courtyards in between. We have a retractable shading for these courtyards, plants. And the idea was, in nighttime hours, we ventilate the building to take benefit of the thermal mass. During day, we have ventilation through, we call it earth duct. So it's a non-insulated air duct, more or less buried in the ground. The idea is to pre-cool, preheat outside air. It's more or less conditions you can compare, like in a basement. It's warmer in the basement in winter than outside, and cooler in summer. And exactly this effect, what we use more or less for preconditioning this air. In the whole system, there is no fan. We use more or less a thermal fan and wind-driven fan on top. So we more or less stole the idea of this wind catcher and combined it with a solar component. So we have a solar absorber, a massive material, a glazed, more or less, part in front of it. So we overheat the exhaust, use the prevailing wind, and so we can ensure a certain ventilation of the space. So there's no mechanical part in it, nothing. The whole thing was done for roughly, don't know Norwegian kronas, but roughly 500 euros per square meter, which is extremely cheap. So here you see the air inlets, and then it goes down at a certain depth, runs up and then up. We have plants, and here you see the retractable shading, or the beginning of plants. And it's really a nice setup. Here you see this solar wind tower with the spoiler on top. So we made the experience that, let's say, the construction culture is a little bit difficult in these countries. So, for example, we had roughly 80% of the spaces which works very well. 10% doesn't work at all. So we went there and checked it, and at this 10% we figured out that they had too much concrete, and they put the concrete in our air ducts, so they were filled up with concrete, so there was no ventilation at all, and a couple of other stuff. So maybe in future we have to be a little bit more careful, a little bit more space for our concepts in these kind of climates. So these cloud stuff, roughly 8 years ago, we're doing the exhibition booth for Mercedes-Benz on the International Auto Fair in Frankfurt since 15 years roughly. And the company in charge of that approached us and said, we need a kind of event for a big fair in Frankfurt. related to buildings, and so do a brainstorming and come up with some great ideas. And I'm not sure who had the idea, but it was quite late at night, and maybe a lot of wine was the reason for that. But somebody came up with the idea to do an indoor cloud. And the guys were really appreciated, enthusiastic. They said, "Oh, cloud, great. So let it rain out of the crowd, let it hail and snow." And so we have to slow them down a little bit. But then we did this cloud stuff for this fair, and it was quite a big event. Our staff, roughly 30% are physicists, and they really love to play, let's say, with these kind of physical properties. And when Sejima got a curatorship for the Biennale, she asked us to do, let's say, one installation in one of the Arsenale areas. Those are roughly 800 square meter big storage areas in the old Arsenale of Venice. And we said we are engineers, so for sure we need an architect to collaborate. And Tetsuo more or less did this big adventure with us. And Tetsuo more or less developed this kind of ramp. And the idea was we put a cloud more or less in the middle of the space, and to make, let's say, architecture, to provide a kind of architectural experience on a, let's say, more abstract, more aesthetical way. So from our point of view, from a mechanical point of view, it was kind of a nightmare, because these buildings are, I think, from the 1500, so a little bit leaky. And we did our testing, let's say, in spring. The Biennale was in summer, so we had fairly different outside conditions. And more or less each guy from the office shown up on the Biennale said, "Oh, what a nightmare." You cannot say to anybody, because the results on the Biennale itself were really not as good as we had it in our test environment. For sure, we tested on 60 square meters, now we had 800. We had a very leaky environment, we have lots of people walking through. And the people loved it, so I think the most critical persons were more or less from our office. But the idea was more or less to have this cloud at a certain height, and you go up the ramp, and then you go through the cloud, and then you go back again. It was really nice, and from the top view, it was quite okay. Tetsuo, I made my first experiences with Japanese architects with Sejima, and Tetsuo is more or less following her line. And what I learned quite early or quite fast was that there is no compromise. Never, ever. And for example, I'm not sure if you see it here, there's a column. And Tetsuo designed the column 30 millimeters by 30 millimeters. It's a L-shaped and when the Italian structural engineer, more or less in charge of the whole Biennale, saw it, he said, "No." And I think till now he says no. So Tetsuo hired a Japanese structural engineer, and it's really an amazing guy. And he convinced Tetsuo in a deep Japanese discussion, and I cannot follow, that he has to use more or less 45 times 45. And that was the only compromise, let's say, for the whole project. So at the very end, we had to limit the numbers of persons, more or less being on the bridge at the same time. And we have to check all the weldings each second week. That was more or less the requirement of the Italian structural engineer, and we never got a permit for that. So I'm not sure if anything had happened from a legal perspective, who is in charge of that, but it works very well till the end. As a follow-up of this experience, we thought it would be great to collect some ideas on skins, because we're using more or less the same material since 2000 years, more or less. So maybe it's time for something new. So the idea was to do a competition focusing on skins, and I only put a couple of the contributions here because I think it's great stuff underneath it. So Athens, the Piraeus Tower. You might have a look on this website. So it's www.cloudscape.es. And I think there are still all the contributions to the competitions, comments, and so on. And here is a nice idea about shading and a different appearance during the day. But the thing I really like most, that's a high-rise from the 70s in Athens, and that was the proposal as a refurbishment. I'm not sure if you have your working place in there, if you would enjoy it, let's say, for more than a couple of weeks, but as a picture, as a principal idea, I think it's really gorgeous. Thanks a lot for your attention.